Hello everyone, and welcome to this video short where we're going to explore a fun divide and conquer problem example and look at ways to analyze a divide and conquer by exploring a recurrence. In this example, we are going to look at the Tromino game. So the Tromino game is a very interesting game here, which consists of this 8x8 board, where we want to fill it up with Trominos, which are these three L-shaped squares, right, such that one square is missing, this black one indicated here. So for example, a solution might look like this, where we again lay out a whole bunch of these Trominos, right, such that this black square is vacant. So here is a solution for an 8x8 grid. Can we find solutions for other grids of other sizes? Let's say ones that are multiples of 2, such as a 4x4 grid, or a 2x2. Which of course the 2x2 solution is pretty simple. All right, well, one way we can explore this is looking at it from the strategy of divide and conquer. That is, here we have a large problem, let's say a 2 to the n by 2 to the n board. Can we solve this in terms of smaller subproblems? That is, can we identify a relationship between subproblem and the global problem itself? Right, and as we noted here in this previous example, some of the smaller subproblems, when you get to a small subproblem, the solution becomes easier to find and easier to compute. So if we could break this larger problem down into, right, a group of these smaller subproblems, we could, in theory, employ a divide and conquer approach to solve the subproblems and then combine those results to get a larger problem solution to the global problem at hand. All right, so let's try it. What happens if we divide our board into 4 smaller boards? We get 4 4x4 boards. And if we were to place a Tromino to straddle all of the boards here, we would get similar subproblems. That is, we would get 4 different boards where one of the squares were essentially vacant in each of those boards. All right, now we have smaller, right? We have a smaller but similar problem. We have 4 of them on 4x4 boards. So what if we do this again, right? Then we get more 2x2 boards, right? 16 of them. Again, we place the Tromino at the intersection or sort of at the border of all the boards. So each of the other subproblems have one square missing. And then we have now a whole bunch of, right, 16 that is, right, subproblems where we have an easy solution. We just place a Tromino and it fills the board. Right? And all we need to do now is combine the results and we have a solution to the larger problem. So how did we employ divide and conquer here? Right? We divided up the larger problem into subproblems and we kept splitting it up into smaller and smaller subproblems until we got to a small enough subproblem that was really easy to solve. Right? That's our base case. So we recursively divide our problem into subproblems until we hit this base case, the case where we have a solution to the problem. We solve the problem directly, and then we need a way to merge or recombine the results so that we get a solution to the global or larger scale problem. Right? In this case, it was just simply putting those smaller boards back together, thus giving us our total problem solution here. So again, starting here, we divide into subproblems until we get to our base case. We solve it directly, recombine the results, giving us the global solution. All right. So from a time complexity standpoint, how do we analyze an algorithm like this? Well, we need to incorporate the time it took to divide the problem into subproblems, right? The time it took to combine the results, and the total time to recurse on the smaller subproblems. So splitting this up, we have the time, t of n, so time complexity function here, t of n, the time it takes to solve a problem of size n, is equal to the time it takes to divide the problem of size n, plus the sum of all the times it takes to solve the subproblems S of I. Right? S of I being the size of the subproblems, plus the time it takes to recombine the results back into our n-sized problem. Note here that this is a recursive function. That is, we're defining t of n in terms of t of n, right? Intuitively, because we're breaking up our problem into subproblems of the same nature. All right. So coming up with a closed form expression for this is not clear because it is recursive in nature. So how do we solve it? How do we get a closed form solution? Well, there are several techniques to doing this. In fact, if you recall from discrete mathematics or reviewing discrete mathematics, solving a recurrence is something that comes up a lot and is an important tool to have in your tool chest when analyzing algorithms. Right? Sometimes it's pretty straightforward. Sometimes it's a little bit more complicated. Here we'll look at one approach, which is using a tree-based method to solve this, or the tree solution, to illustrate and diagram out the flow of the algorithm, which will help us come up with a closed form expression for the time complexity. But there are other ones. There's the guess and check, where you can just simply guess an upper bound and then check it using a proof, such as proof by induction. Right? There's substitution, that is, you can sort of roll out or expand the recurrence, right, until you can identify the actual closed form expression for the recurrence. But let's take a look at the tree method here. Right, the tree method is something that we can explore looking back on our example of merge sort. So if you recall merge sort was our divide and conquer sorting algorithm, where we split up our method into, we split up our sorting problem into a bunch of smaller sorting problems until we got to our base case and then recombine the results. If we were to derive a recurrence for merge sort, we would get t of n is equal to t of n over 2, and that's because we split up our list into two sublists, so the subproblem is of size n over 2, and then we have to solve each of those two, so it's 2 times t of n over 2, right? And then the time it takes to recombine the results is simply n, right? You just simply have to scan through those two sublists and then put them in order as you merge and recombine the results. All right, so this is our recurrence for merge sort. How do we solve it? Well, let's use the tree approach. What's the tree approach? Well, here we diagram out the flow of our divide and conquer approach using a tree, where we start up here with our list of length n. We split it into two sublists of size n over 2, and then we repeatedly do so. Note here, to get from our problem of size n down to the base cases, a list of just length 1, right, we're going to have to divide log base 2 of n times. So note here, the depth of the recursion is log base 2 of n. The total size of the items along each of these depths and the total time it's going to take to do the combining at each of those steps is n. Thus, summing up all of these steps, we simply get something proportional to t of n is equal to 1, right, starting the sum of 1, summing to log base 2 of n itself. And this simply just gives us n log n. Right, so this is one great way to analyze the time complexity of a divide and conquer approach. This is called the tree-based method. Thank you for joining me in this video short. I hope to see you in the next episode.